Kia ora, Year 12. This video is for Tim and anyone else who wants to go over the trig thing that we looked at in class today that I got grumpy about. So it's the idea that we can take two separate trig functions and very usefully write them as one trig function with a horizontal shift and a different amplitude. Mechanically, this is pretty easy to do. We're going to use the compound angle formula to expand this out, and then we're going to match up the coefficients. I'm just going to change the pen colour because that yellow is horrible. So here, this is equal to 1 sine theta minus 4 cos theta. And we're going to look at GeoGebra to see what those two curves look like. Okay, so the green curve is sine theta, and the blue curve is negative 4 cos theta. If we want to solve any equations with two wavy curves, it's going to be a big messy problem. So suppose we had to solve that. Yuck, right? We've got to do something with it. If you're doing level 3 and you don't learn this technique, what you'd have to try to do would be to change this around to sine of pi on 2 minus theta. But then you're still going to have a bit of trouble because you've got this 4 sitting here. But the technique that we're learning here will work even with a pesky coefficient in front here. And it works because of this. If I take those two separate curves and I add them together, I get this beautiful red curve, right? So I get a single curve. So what we're doing is we're finding the equation for that red curve. And if I go back to the first slide without pausing my video this time, what we're doing is saying that that new curve has got an amplitude of r and it's got a shift along of alpha. Right, so how are we going to start this? Well, if we're given the form that we want to work towards, all we do is we expand out this and then we match up the coefficients. So we get r sine theta cos alpha minus r cos theta sine alpha. And it's worth, if you're just doing this for the first time, rewriting it in the order r cos alpha sine theta minus r sine alpha cos theta. Then we've got two equations. By matching the coefficients, we know that r cos alpha must equal 1 and r sine alpha here must equal 4. And this is where I draw a right angle triangle and apply Pythagoras. I know some of you are groaning and you probably don't bother to draw the triangle, but I do, and it works nicely. So here's my angle alpha. I don't know what it is yet, but I know that cos of alpha is equal to 1 over r. And I know that sine of alpha is equal to 4 over r. By Pythagoras, this has got a right angle in it, r is equal to the square root of 17. And we can already go back and look at my graph and see that that matches up the red curve beautifully. The next thing I'm going to do is I'm going to use either the cos or the sine equation to do some year 10 trig. So I've now got cos of alpha is equal to 1 over root 17. Alpha is the inverse cosine of this. So alpha is equal to 75.9 degrees. So we're done, right? We've got thing on the first page is equal to root 17 sine of theta minus 75.9 degrees. And if we look at that lovely red curve, you can see that it works beautifully. Look, I've got the amplitude here is just above 4 at root 17, and the horizontal shift goes out to here, and that's 75.9 degrees. Remember that along here, these numbers are done in radians, so I did this in a big hurry, and I didn't get nice pi on 2 and pi multiples going along the curve. But you can see that that crossing point for the start of my sine curve, so I've got a shifted out sine curve, is about 1 point, I don't know, maybe it's like 1.3. And if you think about this in degrees, it looks about right. So it's 75.9 degrees. What I want to do now, because I think this video is working, is to do a slightly harder problem, which uses the same idea. And so here's the equation that we've got. The other thing I've done is just to get you used to it is that in here, the variable is not going to be theta, it's going to be x. And the shift factor is going to be theta and not alpha. But it's exactly the same idea as before. And you've got coefficients of 5 and 12. So you should be spotting a 5, 12, 13 Pythagorean triple in there. Okay, so if you work through that in the same way, what do we get? Well, if we expand this out, we get r sine x cos theta plus r cos x sine theta. What happens now? Well, I do my triangle. Oops, don't want you to see that yet. Do my triangle here, and by Pythagoras, here's my theta. This is 5 and this is 12, so this must be 13. So r works out to be 13, and theta is cos inverse of, what have I got, 5/13, which is 67.4 degrees. So that's fine. So that should already feel really easy, right? You're given the form of the compound angle to use. But let's look at what else we can do with it. So now we've got a function that really looks awful until we realize that this simplifies. What we need to do here is to figure out the maximum and the minimum of f of x. And usually when we did max and min problems in year 11, we did that by differentiating, but that's going to be a really yucky way to do this. It's much easier to say that f of x is equal to this. So what I'd like you to do now is to pause the video and see if you can finish off this problem, and just have a think about why it's now a much easier problem than it was here. Okay, so what we're going to find is that the maximum value is going to happen where this is equal to negative 13. Right, because the lowest possible value here is negative 1. Negative 1 times 13 is negative 13, plus 17 will give me 30 over 4, right? And that equals 7.5. So that's going to be the maximum value. What about the minimum value? Well, the min is where we have f of x is equal to 30. Don't know what's happened there. 30 over 13 plus 17, which is equal to 1. So that will be the lowest possible value. The last thing that we have to do is to figure out where that happens. But let's just look at that function, and then we're going to sketch it to see where we get the max and the min. So this is a really easy curve to draw, right? I've got my axis here. I could do a nice ruler, but no. My starting point here is a sine curve that's been shifted back that way to 67.4. So it's going to go like this. And I need to figure out where is this value going to happen for the max and where is this one going to happen. Now we know by the features of the sine curve that if this is at negative 67.4 degrees, then this is going to happen 90 degrees on. And here, this is going to be another 180 up from there. Okay, and if I told you that we just wanted the values in the domain 0 through to 360, you can see from looking that there's only one of each. And the number here is going to turn out to be 22.6 degrees, and the number here is going to turn out to be 202.6 degrees. So let's just go back to that exam question and have a look. So this is from an old Oxford-Cambridge question in an old textbook that I found. But it's a very gettable question as long as you see that you've got to turn this into a single trig function. And then you just apply some really basic ideas about sine curves. Okay, that's enough for one video. That's quite long already. Thanks for watching. This has been done in PowerPoint instead of in OneNote, so I wouldn't mind a bit of feedback on how you found it and whether the sound quality is okay. Thanks very much for watching.